Hey everybody, thanks a million for turning out. Amazing conference, amazing people, and so glad you could all make it today. My name's Eoin Wickens, and this is Marta Janus. We are researchers at Hidden Layer. We work in the Synaptic Adversarial Intelligence team, or SI for short. Now, we've been researching adversarial ML and AI security for the last couple of years. And I guess we spoke here last year. I'll go to that in a second. But today our talk is Insane in the Supply Chain, Threat Modeling for Attacks on AI Systems. Just want to apologize in advance that we will more than likely not have time for questions today. We really overshot the slide count this time around. So yes. Cool. So you might remember us from such talks as Sleeping with One AI Open from BSidesSF last year. Huge shout out to those of you who are return visitors. Last year we kind of introduced attacks on AI and machine learning. This year we're drilling down a little bit more into the supply chain. So more specifically, we're going to be talking about, first an introduction, I guess, then supply chain attacks as a kind of a broader overview within the traditional sense, and then we're going to look at different ways that the AI supply chain can be attacked through data poisoning, hijacking of models, exploitation of tools and services, and a little bonus snippet on LLM indirect prompt injection. So it has been a hell of a year. Since this time last year, LLMs have really taken the world by storm. They're being integrated into almost every product and service imaginable, and this is fantastic. It's really at the start of something, and it's only going to grow. Multimodal models made a big appearance. This is, I guess, just a far more comprehensive tool for all of us to use where it can understand different data mediums. And then there's been a huge push with the democratization of AI as well through open source models, where they're really competing with enterprise solutions. Things like, retrieval augmented generation are super popular, even a billboard in San Francisco talking about RAGs, which is still baffling to me from a small coastal island off the coast of Ireland. But here we are. And then finally, things like humanoid robots as well, which really seems futuristic. So speaking of open source models, one rudimentary but very tangible metric that we use to track the adoption of AI is by looking at the number of models on Hugging Face. So for those of you that don't know, Hugging Face is kind of like the GitHub of machine learning. And it's a place where individuals and organizations can share models and data sets and host them with compute and everything. Now, this time last year, almost to the day, there was 176,000 repositories up there. Today, there is 640,000, but it's not stopping there. We're seeing that number grow minute by minute, day on day, and we have to ask a few questions. How many tomorrow? How many next year? And how many are going to be there in the next decade? I'm not even going to tell you how long that animation took me to create. So one statistic that jumped out at me yesterday, actually, when Chenxi Wang was doing her opening keynote, was that ChatGPT took 5 days to reach 100 million users. That is just beyond comprehension. And this rate of adoption is beyond anything that I certainly have ever seen. And nothing stands still. AI is no different. What we see today is just a glimmer of what we're going to see in the future. And that's hopefully what I showed with the last slide there. And whether you like it or not, our future has been redefined, and we have basically entered into a new industrial revolution. Now, the issue is, how do we secure this and prevent attackers or bad actors from using AI or our own AI systems for their own illicit gain? So we need to ensure that our future remains a positive one. So to look to the future, let's first look to the past. So we've been pretty hit by some pretty major supply chain attacks over the last few years. I'm pretty sure that every single one of you has dealt with or triaged some stuff from or the fallout from one of these attacks. They're pretty hard scars to forget. From NotPetya in 2017, causing, huge damage to giants like Maersk and billions of dollars in damages, to SolarWinds, which I remember that one. That was not great. But it's basically a compromisation of the build system that produced the Orion IT management software. And that's kind of interesting, because we'll talk a little bit more about that, or similarities with that later. I mean, the fact that their CISO got charged by the SEC is, a pretty stark indicator of the severity of basically the role that we all play in as a cybersecurity professional in organizations today. We've seen things like Kaseya distributing ransomware, Log4j, which was a massive open source supply chain attack, the Okta breach, and most recently the XE backdoor, which we're still trying to figure out the extent of the damage. So what makes these attacks so devastating? And what is the common denominator that is making these attacks ultimately so successful for the adversary? There is two key things. One is the trust between the producer and the consumer, and the other then is the reach. So this is the one-to-many relationship between the producer and consumer. This can make anything from basically a platform or product that is used across the industry to be a really lucrative target for the adversary. Now, these two properties also apply to things in the AI supply chain. But what is different about it compared to our traditional software supply chain? Well, it's the same, but different. Three main components that we consider when we're looking at the AI supply chain: data, models, and tooling. Data is the data that goes into a model. It's what we use to train it. The model is the result of the training, the result of vast computation across this gigantic data set, which is often bundled into applications or deployed on endpoints. And then finally, the tooling, which is what enables its development, its deployment, and its monitoring. We have a diagram here of the ML DevOps lifecycle. We're not going to drill into it because we don't have time. And we would have had to add another 20 minutes if we wanted to talk about all these phases. But it's very similar in nature to the DevOps lifecycle. For the sake of what we're going to be doing today, we're going to focus on four key things, four key stages within this lifecycle: data collection, training, deployment, and monitoring. What we're going to be doing, just a little heads up, is we are going to essentially threat model around a specific scenario. So we're going to propose a scenario that you probably would see or hear of somebody encountering, and then the risks that are involved with that specific scenario align to these four different stages. And we'll come back to that in a second. So let's go back to data. How important is it? Well, like humans, models are what they eat. And if you put garbage in, you're going to get garbage out. Now, what this means ultimately is that if you feed or train a model on bad quality data, you expect bad quality results. And ultimately, models mirror what you feed it. So data is usually comprised in a data set. What is a data set? It seems kind of obvious. Usually we think of them as things like images, text, tabular data, but data sets don't always take this form. You can think of data as a website. You can think of it as a GitHub repository. You can think of a data set as a collection of references to other pieces of data. And when you think about that, it opens up different attack vectors. One such attack vector was this. It was dataset poisoning, proposed by Carlini et al., where they had a paper basically poisoning web-scale datasets. They were able to basically abuse this dataset format here, where instead of hosting the images for instead of having the images in the dataset, it pointed to a URL. So what they did was they brought up URLs where the images were hosted, and they were able to start poisoning the dataset. And they were able to poison about 0.01% of it for $60. Doesn't sound, too costly, but this 0.1% is enough to have a really significant effect on the classifier. So that's quite interesting. Other real-world examples are things like Poison GPT. We saw a tool called Nightshade allowing artists to poison their own work, so that when an AI provider built a model on their work, it would end up in effect disrupting that training process and causing label mismatches. We saw recently an attack where millions of malicious repositories were uploaded to GitHub. Why would that be? Well, what happens if you're training a model to write code based on all these GitHub repositories? Well, they're going to introduce vulnerabilities. And because they're introduced at the start of the supply chain, when that filters all the way down, you're going to see more vulnerabilities in enterprise applications, since we're relying on these LLMs and copilots, et cetera, to do more and more tasks for us on the daily. Also, within the realm of data poisoning, we're using RAG an awful lot these days as an industry. RAG is retrieval augmented generation. It's where you or I could take a load of files, we could put them, basically convert them into embeddings, and then when our LLM is queried, it feeds us back information based off our documents, and it allows it to kind of give us more accurate response based on our data set, or our data that we feed it. Now, RAGs can be poisoned as well. And if we're able to do that, then it's quite detrimental to any of us here. So one thing here was they were able to achieve a 90% attack success rate when they injected 5 poison texts into a database with millions of texts. So there's a massive ratio disparity here. So a realistic scenario. I want to fine-tune an LLM to create an internal programming copilot based on our company's specific use case. So let's say I'm doing a load of coding in one particular language for a specific use case. Data collection. I scrape 100,000 GitHub repositories and internal code repositories to create a code generation model. The training side of it is I'm going to fine-tune an existing LLM model based on the data that I've gathered. Then I'm going to deploy it internally across a number of different and important engineering teams. And then finally, in the monitoring phase, I start to notice that the model is introducing bugs and vulnerabilities into the code, which are making their way into production systems. So what can we do about that? Well, we have to ask a few critical questions. Data collection. Where did I source my data from? Now, you wouldn't want to, source your data from a subreddit, for instance. You wouldn't want to source your data set from random repositories across GitHub because you haven't curated and tailored in the data set or ensured that they're free of vulnerabilities. You really have to have a critical eye there. Is my model going to learn bad habits from this data? As we said, garbage in, garbage out. If your model or if your data set has vulnerabilities in, your model's going to reproduce those. It doesn't have the intellect to be able to correct for those on the fly. And ultimately, the question we should probably be asking at the beginning, are there vulnerabilities in the code examples in the data set in the first place? When we consider training a model, who built the model that I want to fine-tune? What was it trained on in the first place? And was it even built for code generation to be a production-ready system? Within deployment, we need to be looking at things like, will it produce erroneous output? So will it produce vulnerabilities? Has the model passed all possible evaluation checks? And has it been evaluated by a security team? We're seeing a lot of shadow AI these days. It's great to be able to implement things really quickly, but if it's not going through rigorous testing and stuff that we would subject our own code to it, then this can be kind of an issue here. Now, obviously, we have vulnerability assessment in code databases anyway, so that's good. But within the monitoring phase, am I monitoring the performance of this model post-deployment? Have I, done something by accident like test on the trained data and it's giving me 100% success and this is producing perfect results every time? Or am I performing vulnerability assessments on the generated code? So just keeping an eye to be continuously checking in on the health of your systems, especially in case of things like drift. So that's me for the time being. I'll pass you to my co-host, Marta, to take this over. Cheers.
So we looked at the data poisoning issue. Now we're going to look at the issue concerning the models, trained models themselves. So model hijacking and model backdooring mainly. So first of all, let's define a model. What is a model? Like Owen said before, a model is a result of huge computations run over really gigantic data sets, usually. So in case of generative AI and LLMs especially, those data sets can be really, really, really huge, and the computations can take a long time. And what comes with that, also a lot of financial resources. So put together those computations, those mathematical algorithms, the data sets, money and time, give it a big shake, and you get more or less a trained machine learning model. That's on the surface. And under the hood, a trained machine learning model, it's basically code. And to be more precise, it's usually a huge chunk of binary data which is wrapped up in one of another serialization format. Those serialization formats are inherently insecure. Not all of them, but a great many of them. Some of them were developed much earlier, before machine learning became even a big thing. So they were used for serialization of much smaller objects. They are not really designed for storing this kind of this amount of data, and they were, well, simply saying, they were just designed for different reasons, and they are not really very good at serving us at machine learning. Most of machine learning frameworks have their own serialization formats, preferred serialization formats, and they often stick to those formats, even if those formats prove to be vulnerable. We touched on this issue last year a little bit. Now we're going to look at it in a little bit more detail. We're going to look at how those models can be exploited and subsequently used in supply chain attacks. Like I said before, lots of those formats are insecure by design, and the problem is that many vendors, developers of those formats, they don't really consider those insecurities as vulnerabilities. Often they just say, well, that's how it was designed. It was designed for a different purpose, and at that time it was a feature that was used by people and was like maybe not necessary, but something that people like to have. We often just get an answer like this one down on the screen from Google regarding TensorFlow. It's a feature. We're not going to fix it, and if somebody falls. If somebody gets exploited in that way, it's their own fault because they were using it in a wrong way, which is basically shifting the blame to the user instead of actually trying to do something about it. Another big issue here is that we think of machine learning models, we don't really think of them right now in the timeframes of software. So for traditional software, we have all those security measures that we came up many years ago, like digital signatures to prove that the model is actually comes from the source that we think it comes from, to prove the integrity of the model, integrity checks, even simple things like hash sums. Obviously, running a hash sum on a model that is like 100 gigabytes is going to take a bit of time, but still, this is something worth doing if we are using models downloaded from the internet that we don't really trust. There is no malware scanning, or very scarce. Actually, there are steps being taken in this direction already, so that's something that changed during the last year. But still, many anti-malware products will not touch machine learning models because they are just so huge, and it takes so much time and resources to thoroughly scan. And some of those products don't even know what specifically to look for. So those are all the considerations that we have to take into account when we are thinking of downloading a model from the internet and using it in our environment. And yes, last year we showed, we demoed some cool stuff. We actually exploited a machine learning model, pre-trained ResNet model. We embedded some malicious code inside it, and upon loading, the model was executing ransomware. It was very easy to do for us, but I think for the attackers, it would be also quite easy. So we decided to look at other machine learning models as well. Here is just a quick recap of the Pickle file format. So Pickle is basically a Python module that does serialization of Python objects. It was designed for Python objects and structures, not necessarily machine learning, and actually was not really designed for machine learning stuff. And the objects are serialized to disk as binaries, which are then interpreted by a simple virtual machine that has around 70 instructions. And amongst those instructions, there are a few instructions that actually allow for loading of arbitrary Python modules and executing Python functions with given arguments. So it's very easy to actually inject something into already pre-trained model, a simple Python script that will, spawn a reverse shell or run any kind of malicious binary. And that's what we did in this little example. This one was just printing hello to the console But yeah, that's what it takes. It's really easy. And most of all, the worst thing about Pickle is that this vulnerability, which is not really a vulnerability because it's a feature, it's still there and nobody is fixing it. There is just big red warning on Python documentation website that untrusted models shouldn't be deserialized. But people do that. People just download models from the internet and load them into the memory without much thinking around it. So next, we looked at the HDF5 file format, which is also quite popular. This is a file format that is, amongst others, used by the Keras machine learning framework. As such, HDF5 is not really that insecure. We didn't find code execution from HDF5 by itself, but Keras makes it easy for us. Keras allows you to inject to add so-called lambda layer inside the HDF5 serialized models. And what this lambda layer does is basically designed to for execution of arbitrary to allow for execution of arbitrary expressions. And what that means, it also allows for arbitrary code execution. And especially because those lambda layers are serialized using another Python module called Marshall, which is just as insecure as Pickle. So cracking it took us not much time. We were able to inject arbitrary code in HDF5 Keras model, and upon loading of the model, the code was executed. Now, TensorFlow is another machine learning framework. It's a little bit of a different beast. It uses a file format called saved model, which is based on protobuf. And per se, saved model doesn't, well, so far we didn't find a code execution vulnerability in it. But again, TensorFlow itself provides us with functionalities that can be abused and can be used to create malicious machine learning models. So TensorFlow lets us to read and write files to the disk via machine learning model. It lets us send and receive data over the network. It lets us spawn additional processes. And if you put all these things together, it's like it's super easy to actually create a malicious model that will either exfiltrate the data from the disk or drop a malicious binary, schedule it for execution, or spawn a process from inside the TensorFlow context. And again, we tried to contact Google about it, and what they said, like you saw on the previous slide, was that it's a feature, and TensorFlow is not designed to be used in this way, and people just should run all their models in a sandbox. But do people run models in the sandbox? Not really, no. Another file format that is used for serialization of machine learning models is ONNX, or ONNX, however you pronounce it. And this model also doesn't seem like it has a code execution vulnerability in it, but what we were able to find in it is a directory traversal. So there were already some directory traversal vulnerabilities in it, discovered by other researchers a couple of years ago, but this year some colleagues from my team discovered another ones to the same effect. Those ones were actually fixed, so if you use ONNX, please make sure that you use the latest version. And R is our, one of the latest research from the colleagues of my team, and R is a programming language that was specifically developed for statistical computing and machine learning. So this is something that was not just adopted by machine learning researchers and engineers, but was actually designed with machine learning in mind. But guess what? It doesn't change the fact that it has a code execution vulnerability in it. It's just as insecure as the Pickle and Keras version of HDF5. But in this case, it's one of those rare cases where we were taken seriously. A CVE was assigned to this vulnerability, and our developers fixed it in the latest release. So if you're using R, please make sure as well that you're using the latest release that is not vulnerable to this code execution exploit. So besides exploiting model file formats, there is another way that I thought that it's really important to mention as well, even if it doesn't happen a lot in the wild, or maybe it does, but we don't really have a lot of visibility into it. So it's really hard to tell. But this is something totally different. It doesn't exploit the serialization vulnerabilities. Instead, an attacker could inject a layer of neurons inside a machine learning model, which would totally change the machine learning model behavior. So, for example, in a very simple terms, the attackers could modify a loan approval model to approve all the applications from people named John, for example. This is a bit more difficult to implement, and like I said, the visibility into this kind of attacks is very, very narrow because those things are really, really difficult to detect as well. But it doesn't mean that they are not happening. And we expect that in the future there's going to be some automated tools and perhaps some dark web services that will do exactly that for anybody who is willing to pay. So, like in the previous step, we thought of an example scenario of model hijacking, and in this scenario, we decided not to train our own model because this takes quite a lot of time, quite a lot of money, and especially if it's an LLM or a generative AI model. We decided to go and search for a model on a Hugging Face that would fit our purpose. But we didn't look into that model really closely. We just said like, oh, it's from Hugging Face. It's probably quite trusted. We can just go straight to deploying it across our company endpoints. And after a while, we started seeing some worrying signs like the performance of the endpoints was degraded, and even worse, the company data started appearing somewhere on the dark web. So what could have possibly gone wrong? Yeah, since we didn't really look into the model too closely, we happened to download a model that was either backdoored or exploited in the serialization through the model serialization. So how can we prevent something like that happening? Well, there are a few steps, very basic questions that we have to ask ourselves before we run or deploy any untrusted, any model that was downloaded from the internet. So first of all, have we downloaded from a trusted source? And Hugging Face, as much as we trust Hugging Face as a company, might not be always a trusted source because everybody can upload something to Hugging Face. So we have to also verify that the uploader of the model is a trusted company. And we have to verify that it's really the company that we think that posted, that the repository belongs to the company that we think it belongs to, because attackers can exploit the fact that some companies, for example, don't have a Hugging Face repository, so they can create a Hugging Face repository with the name of the company, with the logo of the company, and pretend that those models belong to this company. I think Hugging Face is started to verify users, so we have to pay attention if the repository is verified. Then we also would like to know if the model was trained on a quality data, because if the model is not trained on quality data, it's not going to perform well. Are there any ways that we can check if the model has been tampered with since it was uploaded? Well, in some cases, yes. Some of the providers publish checksums of the models. So this is something that we should be checking before we download the model. Then, after we download the model, there are additional couple of steps that we should do. So we definitely should treat it as any kind of software that we download from the internet. Meaning, we should scan it for malware. We should check the integrity again. We should check if the model works as advertised, and for the first time, we should definitely run it in a sandbox so we can see if there is any erroneous behavior or any unexpected behavior. And after we deploy the model, it's a good thing to monitor it constantly and see if anything is changing, if anything is going wrong as well. So besides compromising the models, the attackers can also compromise the libraries that were used to create those models, machine learning libraries, machine learning frameworks, any kind of machine learning tools. And if they compromise the build, they compromise the customers. So there is an analogy here to the SolarWind attack in which thousands of organizations were affected because the build was compromised. And over the last year or so, there were a lot of vulnerabilities discovered in machine learning frameworks and tooling. That's because machine learning is just such a big thing right now. AI is everything that people are talking about. So also researchers are looking into those vulnerabilities and trying to find things in anything related to AI. One of the first ones, which is also quite interesting for a different reason, is the shadow ray vulnerability. So is the vulnerability in the Ray framework, which is a framework for AI workloads. It's quite a popular framework, and even big vendors like OpenAI are using it. And shadow ray is a vulnerability which is based on the lack of authorization in the shadow ray in the Ray jobs API. And why is it interesting or actually worrying is that this vulnerability is disputed, meaning that the developer of Ray actually says that it's not a vulnerability at all, and those models, this framework is not supposed to be open on the internet. So users should not put it on the internet, and then there is no problem, because if it's just local, then it doesn't have to have authentication, right? So that's the problem, and the vulnerability is still there. The developers say that it's not a vulnerability, but thousands of publicly exposed Ray servers were found to be compromised. So researchers from Oligo Security found tens of thousands of already exploited servers on the open internet. So you can tell your customer not to use it, doesn't mean that they will stick to it, because that's just shifting the blame to the victim, isn't it? Then we have ClearML. That's another open source framework for ML ops. Also quite popular, and in this framework our team found quite a number of vulnerabilities from code execution on pickle load to directory traversal, improper authentication, then improper storage of credentials, and CSRF and XSS vulnerabilities as well. And all those vulnerabilities put together constitute a allow for a full attack chain, as colleagues from my team described in one of our blog posts. So if you're interested, I'm redirecting you to that blog post. But it's not just ClearML as well. There are vulnerabilities being found in any kind of machine learning tooling. Recently also there were some critical vulnerabilities found in MLflow. Those frameworks are not invulnerable. We really have to pay a much bigger attention to all the vulnerabilities, keep all our stuff updated, and really change the approach that it's a feature, not a vulnerability, because this is not going to work really well in the long run. Another thing is that can be exploited by the attackers in supply chain attacks is dependency compromise. So we saw it happening 1.5 years ago, December 2022, with Torch Triton. Attackers uploaded a malicious library, malicious package to PyPy, and many people actually managed to download it and get compromised before it was discovered and removed from PyPy. And that package was just a simple Linux info stealer that was basically sending the contents of the passwd file on Linux to the attackers, along with a couple of other files. It was nothing super sophisticated, but what we think is the attackers were just perhaps feeling the ground and trying to see how easy it is to bypass to exploit the dependency chain. And the next time, it can be something much more sophisticated. And there is also another thing that was introduced with the dawn of the LLMs, which we call package confusion. Well, we all know by now that LLMs like to hallucinate things sometimes, and they also like to hallucinate imaginary packages, software packages, or libraries. So if a developer asks an LLM to provide a piece of code, for example, the LLM will instruct the developer to download a certain package. And in some cases, we find that this package doesn't exist. But the attackers could query LLMs, check which names of packages appear often in hallucinations, and then actually create a malicious package and upload it to some repository. And how the user can know if it was hallucinated and then hijacked, or it was there and the LLM actually gave a reliable answer. So that's another kind of a problem. With this kind of exploitation, we came up with another scenario. So we have a pre-existing store of data in an S3 bucket, and our MLOps tooling has access to that bucket. Then we train our model using this data. The model is deployed and exposed externally to the customer, meaning that the customer can actually query the model and see the predictions. And after a while, we are seeing some worrying signs as well. What can we do? We should definitely treat all the machine learning frameworks and apps as software, as regular software, and apply all the stuff that we apply to software. We should apply also the access control policies to our S3 bucket. We should check the integrity of the data that we are using to train the model. We should actually, if our model is exposed externally to the customer, it's much more prone to attacks like inference attacks, which we were talking about in our previous presentation, or model theft attacks. So we need some checks on this level as well. If the model is prone, or we should have some checks if those attacks are being actually performed against our model. And definitely we should update regularly all the MLOps software, all the ML frameworks that we have. We should check if there is a proper authentication in our frameworks, and if there are any vulnerabilities discovered, if there are any patches for those vulnerabilities. And as previously, we should monitor the behavior of our model as well. All right.
Cool. Thanks, Marta. So yeah, as Marta's shown, the tooling we use can leave us in hot water, especially if we don't fully understand how it works under the hood with things like those authentication vulnerabilities. The next sections, we don't have threat models in a similar vein, but are definitely super important because they are part of the supply chain. One of these, Hugging Face created a Safe Tensors conversion bot. Safe Tensors is like a JSON-based file format for model serialization, super safe. What they decided to do was create a service to convert all insecure PyTorch models into Safe Tensors. But what we were able to do earlier this year was show that we could compromise this service and basically using a malicious PyTorch model, compromise it so that we could basically hijack any model that was converted through it. That service has converted, tens of thousands, if not hundreds of thousands of models. we were able to basically exfiltrate the Hugging Face user token for the SF ConvertBot account. And then we were able to essentially send malicious pull requests impersonating this legitimate service to any model on the site. And these pull requests were often approved with no contest or anything because it came from a legitimate service. So it's not even about code execution here. It's about the fact that we could ultimately replace the weights entirely of any model across major organizations. And we saw, SF ConvertBot had sent pull requests to anything from Google to Microsoft to other repositories. So we'd encourage to verify that what goes in is exactly what comes out. I know we're tight on time, so I might speed run the next few slides. But Adrian Wood at DEF CON AI Village last year demonstrated that organization confusion that Marta mentioned earlier. Created a fake user account for a couple of organizations and then had users from those organizations join and download models and won some good bug bounties there in the process. So, be careful who you are downloading your models from and make sure that they are verified on Hugging Face. Because that's definitely a worrying concern. One of the really interesting ones is indirect prompt injection as a supply chain attack. And it's not as obvious, but it's quite cool. So indirect prompt injection is essentially where instead of typing in a prompt injection into the chat window, we prompt inject a model through maybe a website or a piece of audio or something like that, or an image, for instance. This can be done especially through things like multimodal prompt injection, which we'll just cover briefly first. A multimodal model is a model that can take in any form of data or different forms of data. And they are subject to multimodal prompt injection, meaning if we pass in an image, it also has a great likelihood of prompt injecting a model. So what happens if you have a website which hosts some of these images, such as what Bagdasarian and Nasi described at Black Hat EU this year? If you upload let's say a compromised image to somewhere place like Wikipedia and an AI-enabled chatbot browses that, well then what happens if this accidentally prompt injects the model? And will image-based adversarial examples be in vogue once again? And how do we threat model for this? This is an open question, but really interesting when we think of a real AI-enabled world. I'll pass you back to Marta to close us out for the final bits.
So we just have 4 minutes left, but it's just the boring stuff that is there, so I'm going to speed through it. So on a positive note, our research and the research of our fellow researchers from other companies as well is making ripples in the industry. We can see that there are some steps in the right direction being taken. Keras, for example, doesn't by default doesn't allow deserialization of lambda layers to avoid the code execution. Obviously, Hugging Face fixed the conversion bot as well, so right now it's not vulnerable anymore. Also, Hugging Face is implementing a rudimentary malware scanner on their models, which is really good. Really good that they are doing it, but it's just the first step. And then we have a lot of regulatory frameworks and security frameworks for AI. MITRE Atlas is one of the biggest ones. It's based based on the MITRE attack framework, which probably most of you are familiar with. So it encompasses some tactics and techniques and case studies and mitigations for attacks that are specifically targeting AI systems. Then there is OWASP, who is doing a lot of this space as well. So we have top 10 risks for machine learning, top 10 for LLMs, OWASP AI Exchange, and these kind of initiatives. NIST, the Artificial Intelligence Risk Management Framework, which is, I think, was one of the first that were published. And also on the regulatory level, things like the EU Artificial Intelligence Act or the ISO standardization, ISO standard 42001. The thing that was mentioned already at this conference is AI bomb, so the bill of materials, or machine learning bomb, ML bomb. Those things are being actively looked at and developed as well as the AI security posture. So things that we apply to traditional software now, they are being ported to encompass the AI space as well. And we are in the process of trying to set up some kind of model signing, so digital signatures for machine learning models to prove the integrity, the provenance, and the fact that the models were not tampered with, as well as tracking the lineage of changes in machine learning model, which is right now a really important thing with all the fine-tuning of LLM models and stuff like that. And the takeaways really quickly. So we have many places in the AI supply chain where the attackers can strike. So we have data poisoning attacks at the data collection, hijacked backdoor models at the model sourcing. We have vulnerabilities in compromised packages in the MLOps tooling, and something that we didn't cover in this presentation, prediction tampering after the model is deployed. And how can we secure against it? Well, we first have to take a step back and apply all the security measures that we apply to software also to the machine learning models. That's the basics. We have to build on top of it very sophisticated solutions that are targeted just for machine learning, for AI solutions. But before we do that, or during doing it, we have to go back a step back and apply all those things that we apparently forgot to apply before.
All right, we're over time, but last year we said, don't worry about Skynet, it's in the future. This year, we have humanoid robots coming out from every major company. We probably want to secure this stuff now rather than later, because we'll end up in an iRobot or a Cylon situation. So thank you so much, everybody, for coming today. We really appreciate it. And please do reach out to us if you have any questions.